Good evening, ladies and gentlemen. We welcome your comments and requests regarding this series at info@isic-japan.org. Today's program features simultaneous interpreting in English and Japanese. To change the audio channel, click the interpretation icon at the bottom right of the Zoom screen. This program is organized by ISIC Japan, produced by Bloom Pacific, and sponsored by BAE Systems and Raytheon Technologies. The interpreters are Christopher Field and Paul Hersey. I would now like to turn the floor over to ISIC Chairman Masanori Nishi to chair this Defense Industry Forum on the topic of Return of the JEDI, Emerging Technology and Data Strategy.
ISIC Japan のウェブセミナーにようこそ。
Welcome to ISIC Japan. I am the chairman, Nishi Masanori. Today's seminar is entitled Return of the JEDI, but we're not going to be talking about Star Wars. This refers to the joint enterprise digital infrastructure being planned by the U.S. Department of Defense. This will be our starting word as we move into tonight's discussion. The biggest issue for modern security today is how to understand emerging technologies and how to handle the vast amounts of data that result from them. In the past, when I have heard such statements, I felt as if I vaguely understood them. But specifically, which technologies are important for what purposes? And how much data is going to accumulate when we start to use those technologies? Tonight we have two guests, one from Japan and one from the US, who will talk about this subject. Nishiyama Junichi-san is a fellow at the Institute for Future Engineering. He had a long career working on defense-related technologies at Mitsubishi Heavy Industries, MHI. Our other guest is William Schneider-san, who is a fellow at the Hudson Institute with long experience in the defense field, including as Undersecretary of State and Chairman of the Defense Science Board. We will start with Mr. Nishiyama, who will talk about some technologies recently in the limelight. Mr. Nishiyama, please. I am Nishiyama, who just was introduced. It is an honor for me to be able to speak to the ISIC webinar tonight. First of all, the theme or topic that I'm going to talk about is called Emerging Technology and Data Strategies. Next page, please. Next page. First of all, I'd like to talk about an overview of innovation initiatives in each country. In the US, as you probably know, there is something called the DARPA Challenge to promote innovation initiatives. It started with the grand challenge of automated cars, self-driving cars. There are many challenges that they have taken on, which have become well known in Japan. One of the continuing challenges is called the Spectrum Collaboration Challenge to make optimal use of the electromagnetic spectrum. There is another one called the subterranean for underground exploration. There's also the launch challenge and several other challenges which DARPA has been undertaking to promote innovation. Next, I would talk about the Defense Innovation Unit. This organization was started in the Obama era and seeks to incorporate commercial industry, Silicon Valley type of technology for defense purposes. In addition, the Department of Defense has something which relates to today's theme, the JEDI, Joint Enterprise Defense Infrastructure. There was a competition which ended up with their forming an alliance with Microsoft. So this is the company that makes our operating systems for our computers, but they are also participating in the defense industry. Next, turning to Europe, there's something called the UK Catapult. This is an innovation project to overcome challenges. The country of United Kingdom, England, seeks to support technology innovation. And then in Europe as a whole, there is also something called JEDI, which is the Joint European Disruptive Initiative. So they're looking for disruptive technology, which Europe is seeking to support. In China, you are well aware of the civil-military fusion policy, which seeks to join the technologies of the military and private industry. They have something within that called Manufacturing 2025. At the point that they will facing towards their 100-year anniversary of the founding of their country, to seek to be leaders in world technology. And for that purpose, they need to dominate or take a strong position on among the international standards. So they want to have what they call China Standards 2035. So what is Japan doing in this context? In Japan, we have not put national security at the front of this effort, but we do have an integrated innovation strategy of 2020, which seeks to further their goals of advanced technology. So all of these countries and regions are placing a lot of emphasis and efforts into innovation strategies. Next slide, please. So what is emerging technology? I think that you have among you many different ideas of what this might be. It's a very broad spectrum. I would like to introduce a few examples. First of all, in 2017, at the Davos meeting, there were 12 emerging technologies identified. Then in the RAND Institute in the US also is working on the Security 2040 project, which includes artificial intelligence, speed of change, 3D printers. These three areas are the areas of research for RAND. And they're also looking at the differences between generations in thinking. This is not a technology per se, but that's what's pointed out by the word millennials. Next, in 2019, the U.S. House Appropriations Committee added budgets for 5 different areas: quantum information science, artificial intelligence, cybersecurity and privacy, metals-based additive manufacturing, which is metal 3D printing, and 5G communications. Further, also in the United States, in October of last year, there was a national strategy announced for 20 critical and emerging technologies, called the National Strategy for Critical and Emerging Technology List. In Europe, in 2019, they announced a list of future 100 radical innovation breakthroughs for the future. So there are many, as you can see, technology fields that have been identified as emerging technologies. Next page, please. It's very difficult to narrow these down to a single sheet, but from the standpoint of, I've tried to do that from the standpoint of security technologies. I picked up, or I'm focusing on 9 of these areas. The first is robotics, AI, advanced computing, energy technology, quantum technology, additive 3D printing, hypersonics, and neuroengineering. So I have looked at these 9 fields. If you go back to the RAND study, the Davos, the US Appropriations Committee, and so forth, they're somewhat different. The words don't exactly appear in each of the lists, but I think there is a strong correlation. So robots, robotic engineering, AI, advanced computing, energy, quantum technology, and 3D printers can be seen as areas where each country is in fact putting in efforts in particular. Next page, please. So I have tried to sum up innovative technologies in my slides so far. Recently in the US, there have been announcements about data strategy, and we will be hearing about that, I think, in more detail from Mr. Schneider shortly. Next, please. So when we talk about data strategies, I mentioned earlier the JEDI cloud in the US. Within that context, it's not only the JEDI cloud, but the general subject of big data, which has been brought up a lot in the media. I'd like to talk for a second about what big data really means. First of all, there are 3 V's. The first V is volume, extremely large volumes, quantities. In 2025, we are told there will be 180 zettabytes of data. What the heck is a zetta? I have looked it up on the internet, and recently on the internet we talk about giga speeds, but zetta is tera is 1,000 times greater than that. So we have now terabyte hard disks. And then if you take 1,000 times 1 tera, you get a peta. And 1,000 times a peta is an exa, 10 to the 18th. And then another 1,000 times that is a zetta. So it would be 1 billion times a tera. So in 2025, we're talking about 180 of those zettabytes. A tremendous amount. The next is the V is the velocity. And we know this by how fast we get an answer back from Google query, or sending an email, sending Facebook photos, and so forth. They're all moving at tremendous speed, transmitting at tremendous speed. The next V is variety. There are many, many different forms that data takes now. Those are the 3 V's. Recently, in addition to these, there is a question, or there's more focus on some more V's: veracity, variability, visualization, and value. Those things have been added. So how do we handle big data. That has become a very major issue. Since it's big data, to handle it requires data storage centers, also referred to as data warehouses. These things have become indispensable. And then when you have these large amounts of data, you need new computing technology with very fast speeds. So this all demands more and advanced computing techniques. Next page, please. So what do we do with this data? We don't use it only in our own country. We want to share data with countries of like-minded thinking for purposes of security and public safety. The sharing of data can be used. But when I talk about sharing data, what data and how should that data be used? I have tried to sum up the situation there. I think there's, first of all, basic data, science, research, manufacturing, know-how, Internet of Things, and various such data. There's then, separately from that, real-time data. For example, if we think about it from security standpoint, early warning information, tracking information. Then finally, it may be a bit of a rough way of putting it, but intelligence information. To share this kind of thing for Japan, we want to be able to think about sharing with our allies and friendly countries. Next, please. So what are the conditions for being able to share data? Again, I thought of a few different cases. One is that we assume a cooperative scheme. U.S.-Japan Security Alliance, 4 countries, the QUAD, recently called Quad, U.S., Japan, Australia, India. Another is the 5 Eyes plus 1, U.S. and UK, UK and Japan, sorry, and others. There are many different combinations that we can think about. Then there's also a need to unify our classification of information. For example, top secret, secret, and so forth. What important information should be managed, controlled, CUI, what information is open. I think that sharing requires us to decide on these things, but when we do so, a realistic first step is can be something like GSOMIA, which is a General Security and Military Information Agreement. Using such an agreement, I think, is a realistic first step towards this goal. Next, please. What are the issues? We're talking today about innovative technology and data strategy, but to sum up what I've been saying, first of all, data storage centers, data warehouses are going to be necessary. And now, in order to protect the data, cybersecurity is necessary. In Japan, starting next fiscal year, 2021 fiscal year, we are planning to build something called the Japan Digital Agency, which will handle, I believe, should handle security aspects, national security aspects. And then as we think about sharing data with other countries, we need to have a unified or shared security clearance system, which requires a mutual authentication ability between countries. And then in industrial area as well, we need to have industrial security for the sharing of information between nations on a private basis. In the technological area, the fusion between military and private industry is a difficult subject. The technology driver is often private industry. We need to have technology for military purposes. So how do we make use of that private technology, commercial technology? And that has to be thought about in conjunction with big data, because these new technologies are national security issues. I would like to emphasize today. In other words, military competition is technological competition, or you could say the other way around, that technological competition becomes military competition. That's what I'd like to say today. Thank you very much for your attention.
Thank you very much for that, Mr. Nishiyama. There are various types of technology out there in the world, and they have various kinds of military applications. That was a very clear presentation. Thank you. Our next speaker is Dr. Schneider. So what is big data, and how does treating and dealing with big data have implications for security in today's world? Dr. Schneider, please.
Thank you very much, Mr. Nishi, and I'm very appreciative of this opportunity to be able to discuss this issue of data strategy and the importance of data for the application of advanced technologies to national defense. Next slide. In thinking about this, it's constructive to consider the context in which military applications of data are being developed. Data has become the decisive contributor to the creation of military power in the way that industrial production was in the 19th and 20th century. Data enables the scale and speed to create an operational advantage in its military applications. And the data and the data sciences that enable the user to exploit this data enables military leaders now to integrate all of the domains of warfare into a common command and control system. In the DoD, this is called the Joint All-Domain Command and Control System. In the 20th century, we tended to focus on land, sea, and air forces. And in the latter part of the 20th century, the application of space for defense purposes. But we know that there are other domains that have become increasingly important, and these include cyber operations, operations in the electromagnetic spectrum, and operations dealing with information. I won't go into all of the others in the interest of time, but the data that is generated by military systems and the technologies that make those military systems work is collected, stored, and then algorithmically processed in public and hybrid digital clouds, of which the DoD JEDI and the intelligence community C2E operate both in a centralized fashion, but also at the edge. That is a term applied to where data is collected and exploited. The data is collected and exploited where the data is collected, such as on an aircraft or an unmanned aerial vehicle or a submarine or whatever. Next slide. As Nishiyama-san noted, the scale of data is astonishing and is hard to keep one's head around. But in breaking down this figure of 175 or so zettabytes that are forecasted, 90 of those zettabytes will be created by the Internet of Things. That is, almost every device is going to be connected through the internet, and all of these things will be generating data continuously. About half of the data will be stored in digital data clouds like JEDI and C2E, the intelligence community's cloud. 30% of the data will be collected and consumed in real time. This is very important for military operations, and these data, of course, are largely machine-to-machine operations. And just to get a sense of scale on 175 zettabytes, if they were installed on DVDs, the stack of DVDs would be 23 times the distance to the moon. So it's an astonishing amount of material. Next slide. In looking at the DoD's plan for integrating all of the domains of warfare, the command and control concept is based on exploiting these vast data aggregations, both at the in a centralized location, as in cloud computing like the JEDI, as well as computing at the edge, where the computation is done where the data is generated. And this multi-domain operation that the DoD is planning integrates an operating concept, the command and control concept or construct, the data, and the algorithms. Next slide. The DoD has developed a data strategy framework, and I have cited the URL on the slide for those who may wish to read it. But the data strategy is composed of a vision statement to try to understand what is trying to be achieved, and then some principles of the application of data, and then from that we can extract the essential capabilities that we can generate by the use of data, and then develop specific goals that can be put in place, funded, and operated. Next slide. As mentioned, the JEDI is the DoD's activity. As mentioned, the contract was won by Microsoft. Microsoft has its Azure cloud service. We have two other large cloud service providers, Amazon Wireless Services and Oracle. And the problem has been that DoD has developed the applications of clouds for many specific purposes. The DoD has more than 500 cloud in operation now, but in order to extract the advantage of those data clouds, they really need to be integrated because of the need to communicate across the entire defense establishment to assure that all of the capabilities are being used to their best advantage. And so this is now underway, and it's one of the main instruments for the exploitation of data. I won't discuss the intelligence community effort in detail, but the intelligence community was the pioneer in the application of data clouds for its mission. It started in 2013, and it evolved. Now they have a so-called hybrid cloud architecture that is proving to be quite successful. Next slide. The integration of data, algorithms, and the command and control concepts of operation in multi-domain operations is the key focus of the DoD as they attempt to exploit data for defense purposes. The concept of multi-domain operations is important to appreciate because it differs so significantly from our experience in the say 19th and 20th centuries. It's a concept that enables the joint force, that is all of these capabilities, to achieve a competitive advantage over a near-peer adversary, such as Russia or China, by presenting multiple complementary threats to that adversary that each require a response, and it exposes adversary vulnerabilities and other threats. This is a way of being able to achieve much more effective deterrence of in a military or diplomatic setting than is the case if we had relied on classic industrial applications of the creation of military power that are not nearly as effective. The simultaneous implementation of all of the capabilities of the joint force involves being able to collect all of the data that is being generated by sensors in all of these domains and to optimize the response to threats. Next slide. The illustrations here show the vast amount of data that needs to be exploited and acted upon. In this particular case, we show an illustration of some events in the Taiwan Straits a couple of years ago, but you can see with all of those aircraft and ships operating in the area, data is being collected and processed and being used to guide a response. In the cartoon on the right, you can see how the data being generated in the maritime domain, land, air, and space has these multiple dimensions to it. It's in the electromagnetic environment, it's in the information environment, and it's in the cyberspace environment. All of these data need to be collected, processed, and assessed in ways that can produce a coherent and effective response. Next slide. In thinking about how the evolution of data can be important for the US-Japan Security Alliance, both nations, including our allies, such as the countries of the Quad dialogue, US, Japan, Australia, and India, will need to evolve their command and control systems to enable all domain interoperability and to be able to benefit from the sensor networks both nations have developed. As Nishiyama-san indicated, we have an agreement between our two countries, the General Security of Military Information, which may be the platform that enables the diplomatic platform, which enables us to be able to share information effectively. Combatant platforms such as aircraft, for example, will need to be optionally manned. That is, they can be equipped to be operated by a human operator, or can be operated remotely or operated autonomously. In the military concept of multi-domain operations can be seen as the military parallel to the civil notion of the Internet of Things. The conversion of fourth to fifth generation systems also provides an opportunity to extend the service life of obsolescent systems. For example, we can take older aircraft and remove the human operator and enable them to operate in an unmanned configuration. Such a conversion can extend the useful life of these obsolescent systems. We also need to be cognizant of security. The homeland is no longer a sanctuary. Logistics will be contested, and the supporting civil infrastructure will be at risk from cyber operations and other threats. Emerging requirements provide new opportunities for US and Japan industrial collaboration. Our economies have many complementary capabilities, and the opportunities for our two countries to evolve these technologies together and to apply them for our shared security needs is a powerful opportunity. Next slide. It's useful to recognize that our adversaries are also cognizant of the importance of data to their military operations, and both China and Russia have developed an infrastructure for these purposes. China has developed a strategic support force which brings together cyber operations, electronic warfare, and space. That is a unique form of organization, but reflects China's recognition of the importance of information to warfare. Russia, in a somewhat different way, nevertheless, has also appreciated the importance of information to their approach to military operations, which they call hybrid warfare, which involves a mixture of gray zone operations, as it's called, as well as classic kinetic operations. But information is recognized as being decisive, and data is the raw material from which information is developed. So thank you. I'll be glad to take some questions.
ありがとうございました。ある意味、
Thank you very much. Seems to me that
そこで
the
すみません。
discussion went all over the place. I'm very sorry, but I'd like to ask some questions of our speakers. Mr. Nishiyama, it might be a rough way of saying it, but in the analog era, data was something that disappeared. It went away. But in the digital age, we store data. We can accumulate it over time. So I think that we could say that another way, that compared to the analog era, the rate at which information accumulates has become very much faster. So it's harder to store. But you always have to be checking it and you have to always be processing the data. And so the burden of creating algorithms is very heavy. But storage too will continue to become more and more possible. And so as more and more data accumulates, you have to analyze it in a timely manner. So quantum computing is increasing, and it's anticipated that there will be computers that are far more powerful than what we have now. But with the emergence of these new technologies, data is expected to grow exponentially. We will be able to process it all. I think that will be a new technical question, Mr. Nishiyama. What do you think?
Thank you. It's a very difficult question you've presented, but for me, who believes in technology, quantum computers and AI will support an age where these things can be processed, I believe. But before we get to that, it seems that Japan has the leading supercomputer. That has to be fully realized. So using supercomputers, we look at what we can learn from this big data, applying AI. I think that's the first direction that things will be moving. But nevertheless, huge resources are required. And what I mean by that is, first of all, electricity. These computers use a lot of electricity, so tremendous amounts of power are going to be needed. The computers themselves are large objects. If we can make a quantum computer, this could be solved, but I don't think it's going to be that simple. Of course, when that happens, there's going to be even greater expansion of the amounts of data involved. So the technology that we get from various technologies, as you said, in the analog age, data would disappear, but now in the digital age, it keeps adding up, accumulating, piling up. The pictures we take on a daily basis, the photographs we take, we might have had hundreds or tens or hundreds of photos totally, but now we can have hundreds per day, even on an individual basis. So, of course, this has to be left to the power of computers, I think. Thank you.
Thank you very much. Dr. Schneider, you were on the ground in the field of national security for many years. And so I'd like to get your feelings based on your experience, but for a commander at the last instant, the commander has to make a decision and to give orders. To help the commander make orders, the commander's staff has to deal with stacks and stacks of information and support that decision-making process. But in the last instance, what is the determining factor is the individuality of the commander. So it's hard to get at this, but when you look at the individuality of the commander, does this have an influence on how we process data? In other words, do we have to think about how we influence a particular commander and how we present the information? That is to say, that people always have ways of convincing the boss, if you will. And in the process of processing huge amounts of data, there are AI processes and so forth. But in a very critical situation in warfare, you have to think about the final decision and will it be made by a human, or can we expect that things will begin to depend more on AI for that final decision? Thank you.
Those are very good questions, Nishi-san, and it's the kind of question that is being asked frequently. One of
問
the
いはよく出てきています。デジタルの世界の一つの側面と言いますのは、若者の兵士とか水泳とか、そういう人たちはデジタルの世界で育ってきたので、デジタルネイティブという言い方もあるわけなんですけれども、でそういう人たちはどんどん将校になってきているということで、幹部も大きなデータセットを管理する、ことについて慣れてきているわけです。アルゴリズムによって作り出されているデータを処理していくことに慣れてきているわけです。アルゴリズムの中に意思決定プロセスが入っているわけですけれども、
application of lethal force cannot be made
致死
autonomous.
的な武力の行使というのは自律的で行ってはならない。これは人間が決めるべきであると書いてありますけども、ただその人間の決断への多くのインプット
Exploitation of data that his analog
作られているわけです。50年前のアナログの世界ではそう
So I think we have an opportunity to have our leadership be able to make much better informed decisions about the application
決
of
断を取ることが可能になっています。
decisions about the engineering of systems and so forth that are likely to be much better than would be the case, say, 50 years ago.
ありがとうございます。
Thank you very much.
私自身はアナログの時代で育ってデジタルの世界に入って
I was brought up in the analog world and have entered the digital world. And looking at the way that data is collected, you
私にとって
go to people first who have
人間
information.
処理を
So information to me has always been processed by people. It has always belonged to people. And then you try to get something out of that data that belongs to someone. Of course, in the internet, it's possible to learn a lot of things, to get a lot of information, but it's always the result of some person having processed it. There's always individual bias behind it. Who processed that data and what bias was behind it? There's no evidence of that now. It was a bit easier in the analog era because you knew who you were asking for data and what their particular outlook was. So one problem that we really face now is how do we look at data that is biased and understand how it's biased?
Yeah.
The data process itself is becoming a bit of a black box. How ought we to understand that in processing data? Dr. Schneider, once again, would love to hear your thoughts.
Thank you again, and that is also a very pertinent question that I think almost everyone asks about data. One of the things about data that helps to mitigate the problem of bias is that data is being collected from many, many different sensors. And through the use of artificial intelligence, you're able to exploit different sensors that collect information about the same thing. So it's much more difficult for a user to, as we say, cherry pick the data that suits his purposes. because he's now got the benefit of all sources of data that mitigate the risk that a user of the data or a decision maker decides to collect just what supports his personal bias. So while this cannot solve the problem, it can mitigate the risk of decision makers producing biased results. Yeah.
ありがとうございます。
Thank you.
西山さん、
Turning to Mr. Nishiyama.
日本人の
Um,
そうな質問で恐縮なんですが、
No, I'm sorry to ask a question that
武道をやります。
is a very Japanese one. Let's say we do the martial arts. There are things that an individual can learn, his body can learn, but then there are various stances and personal tricks that you can also use. In war, you always have soldiers, and when you have to rely on the individual's doubts, then what do you do? Classically, you had infantry, and we might have automation, and we might have machines that replace humans in some instances, but there's also information that individuals have developed for themselves. And I think that it should be possible to transfer that individual human knowledge to machines, but can everything always be processed with data? I'm sorry for an endless question, but is it possible for us to convert all knowledge we have into data? Koshiba-san is a Nobel Prize winner with an interesting quote. Einstein was a genius. Mozart was a genius. They're both geniuses, but I, Koshiba, think that Mozart was the greater genius because the theory of general relativity was bound to have been discovered by someone in the field of physics. Someone was bound to eventually notice it. All researchers had that chance, but Mozart's melodies were not something that someone could just discover. So that's what Koshiba-san says, that even geniuses can be differentiated. So there are things that we're able to grasp, able to understand, able to wrap data around, and others that we may not be able to. Sorry for a somewhat abstract question.
ありがとうございますというかですね。
Thank you. I don't know if I should say thank you for this very difficult question, but in Mr. Schneider's talk, as I listened to his answer a moment ago, perhaps I should say it this way. I am a technologist, an engineer. I was building missiles, and I relied on Newtonian physics. If you do A, you get B and C. So it was we were able to solve most problems with Newtonian physics. However, now in GPS, they're discovering that Newtonian physics alone is not enough. We have to apply Einstein's relativity to handle, otherwise we can't compensate for time errors. So in that sense, as you just mentioned, the genius of Einstein it is an extension of things that I can understand. Perhaps this is what you were saying too. So when you talk about the engineer's instinct or special tricks, special abilities, when you touch something, can you, with your hands, feel the difference in 1 micron? I think that, no, those things have to be converted into a computer processable system. When we talk about Mozart, it's a very difficult subject. I don't think that music could have been done by anyone. What I want to say is that when we are able to solve physical problems with computers and to speed that up, increase our ability and our level at which we do that. But what's looked for, what's sought now, and I think this is what you are saying, Mr. Nishi, is for people to understand, who understand society, the logic of that, the algorithms of understanding society. How do you put that into a computer? That's what's really being sought, I think. This is not something I can give you an easy answer about, but that would be my first attempt.
Yeah.
I want to hear Mr. Schneider's opinion too about that very much.
Yes, it's
Mr. Schneider, sorry. What would you think to my somewhat half-baked question to Mr. Nishiyama?
Mr. Schneider, I'd like to ask your opinion about what Mr. Nishiyama just said, my question.
Yeah, it's you are asking very good and fundamental questions about this, and I think while we're discussing data, what we want to create is information. Data is in itself not informative. The data needs to be converted into information that a decision maker can act on. And what is helping us here is that the ability to exploit these vast data sets and extract information from them gives the decision maker much more insight into the environment in which he's making a decision and knowledge about the issues that will affect the outcome of that decision. So you're ultimately converting data to information to decisions, and the ability to more effectively exploit the data resources at one's disposal enables the decision maker to come up with better decisions. This does not say that we will be able to use extensive data to reproduce the genius of Mozart, for example, but there are a lot of things that can be learned about the art of creating music or creating art that gives you a much richer understanding of this, and that I think will help us understand human action and human creativity much better, and in doing so enable individuals with responsibility, let's say for the armed forces, to be able to make sound decisions based on all of the information that's available.
Thank
you very much. So all of my questions were rather abstract. I'm sorry about that. But I worked myself for 40 years in the defense field and dealt with technology. But I do feel that there was very rapid progress. It used to be that depending on the service, you could have communication or not, and the problem was simple. But what we face now is not just the character of the individual land, sea, and air services, but a more fundamental, essential aspect of how data ought to be processed. We're about out of time, but I'd like to call on both of you for a final comprehensive comment. First of all, Dr. Schneider, we've talked about what is data. We've talked about the significance of processing it. I do appreciate your thorough responses, but in conclusion, do you have one general point to make about what we've talked and perhaps related to training?
Sure, and thank you for your comment. One of the interesting things about the development of data and its widespread infiltration of every domain of life is it used to be that the military applications were very different from civil applications of technology. But now we're seeing a convergence. I mentioned the military application of big data is called a joint all-domain command concept. This is the analog of what is being done in the civil sector with the Internet of Things. They both use the same underlying technology, even though the purposes differ. And I think this is a dimension that is moving along very quickly that will make it possible for defense to be much more effective and have serve the purposes of being able to manage a more peaceful world than would be the case if we were dependent on the kind of technologies that we had to live with in the analog era in the 20th century. So I think there's grounds for optimism, and at the diplomatic level, I think grounds for very effective U.S. and Japan collaboration in this area.
Thank
Thank you, Mr. Nishiyama. We had a wide-ranging discussion, especially you were able to share with us a very detailed, multifaceted presentation on data. So to go back to starting principles, you told us about new emerging technologies, Mr. Nishiyama, and that will involve data processing, data collection, sensors. And so as we look at how technology will continue to progress, what is your greatest area of interest, Mr. Nishiyama? You talked about a lot of new areas of technology. Perhaps it's one of those, but as someone who's worked in this area for a long time, what area of technology interests you the most?
ありがとうございます。今日のお話、むしろこちらがいろいろ勉強させていただいたと、こういうふうに思います。特にデータの利用の話はですね、その物理法則だけではなくて、社会科学の知識、知見が必要で、それがないとデータもただの、1と0の山にしか過ぎないと、こういうことかなというふうに、逆にというか勉強させていただいた次第です。それからその新興技術というかですね、次の技術がどういうものが必要かということで、どれに注目するかということになると、一つにせよというのはちょっと酷なご質問かと思いますけれども、やはり、コンピューターかというふうに思います。 ただ、コンピューターもですね、1と0のいわば仮想空間の中のデータですけれども、実際に物理空間で動くもの、エネルギーが必要で実際に動く、つまりマスを動かすもの、この技術がないとですね、実際に物は動かないわけですから、コンピューターは頭脳であって、でも体も必要だと。そういうことでエネルギーとか、それからハイパーソニックって言葉も出てますけれども、極
We
超
talk about hypersonic technology and so forth. Technology which it has to interact with technology that actually physically moves. So if I, but also all these technologies are important, but if I have to narrow it down to one, I would say it is going to be computing. Thank you.
Thank you very much. Both of you have told us about the world of technology, its future, and about the data that will be accumulated through time and how it should be used. Especially for you, Dr. Schneider, thank you for joining us so early in the morning for you, and we look forward to continuing to work together. Ladies and gentlemen, this concludes our ISIC Japan seminar for today. Thank you very much.